Good morning. Thanks for the nice introduction. Well, yesterday we saw a lot of analytical, emerging technologies for analytical, and today we're moving into processing. So my idea here, this is my disclosure, the idea here is not to talk about all the emerging technologies, but to put the consumer, the new consumer, into the technologies and the demands that this consumer is taking into the food industry, and show the benefits of those technologies, and also try to understand or try to discuss it. How do we implement it? Because we've been facing a lot of problems recently in the magazines, and I'll discuss that. So the new consumer is facing different demands from the past. It's, you know, healthy, convenience, safe, fresh, quality, sustainable, and things like this. And and where do our consumer take the information that they need? These are examples in the US, but we see a lot of magazines, we see a lot of blogs, we see a lot of people on TV discussing a lot of things. And what concerns me is, I don't know in the US, but in Brazil we have a lot of actors and actresses on TV, and they think they're all nutrition or food scientists, and they give advice on everything, which is really difficult to reverse the information that they give. So what we see is there is a lot of conflicting information that creates a lot of confusion. And if we see what consumers thinking about the conflicting information, 80% thinks that strongly agree or somehow agree with the conflicting information. And also that this information is somehow making problems or troubles for choices, which is for us quite complicated. And what I think we see recently, it's what this guy called a chemophobia, which is really harmful for what we are facing in terms of food processing recently. And what concerns a lot is that lots of confusion. What is natural? What is not natural? What's the definition of natural or organic or things like this? And the confusion is really bad. In terms of an ingredient, so what's the fact that an ingredient is synthetic not necessarily means that it's dangerous, as well as if it's natural, it doesn't mean it's safe. But the nomenclature is confusing. And something else is also has come to labeling things. So you probably saw that. What happens if we label a banana? What's the consumer thinking about that? And where do we go if we do that? So it's a lot of things there. And again, chemophobia is taking place everywhere. And what concerns me most, being a process engineer, is what the ANOVA classification of food came out with this new term, ultra-processed food, and all the things we see on the newspapers, television, and even at the scientific publications. We see a lot of things describing ultra-processed food. And as a process engineer, and it's my opinion, is not the organizer of these events, it's a huge mistake, considering if you go to the definition of that, the NOVA classification says that ultra-processed food is a formulated food. So formula is one thing, processing is something else. So we should not confuse that. But consumer is really confused about those definitions. And in terms of challenge then, we see the demands of the consumer. We see the needs. It needs to be diet light, free from vitamins, minerals, fibers, and the circumstances that we are consuming today. And we eat it in the morning, in the night, in the week, and the weekend. Our cars, all of them have cup holders. There's no car without cup holders. We eat in the car. So it's a lot of different circumstances and how a process engineer will deal with that. So this is really a complicated thing. So in terms of emerging technologies, of course, I cannot go through all of them, but there are, if we divide them into thermal and non-thermal technologies, and mentioning the ones that are almost ready for market, some of them are still there, we see different ones. And I'm not going to describe all of them, but just try to touch one that's thermal, another one that's non-thermal, and then we can compare and discuss at the end of the section. So in terms of ohmic heating, don't know if you have heard before, but this is still a heating technologies. What's different? The principle of this technology is like we have the electric circuit. We have a resistance, we have a voltage, we have a difference in voltage, and we create a current. And in the case of the food is the resistance. So we heat the food internally. It's a volumetric heating. There's no heating surface. So the food is heated as the current goes through. It's already a commercial technology, and it's not a batch, it's a continuous technology. And as the product is pumped, each time it passes in between two electrodes, it heats, and it heats really fast. It's like more than 10 degrees Celsius per second. So it's really fast heating. And then you have a product ready to be cooled. And what does the technology does to the microorganisms in terms of food safety? Most of the mechanism of inactivation is a thermal effect. So we're killing by denaturing proteins and membranes and things like this. But there is a side effect which is called electroporation. That is created in the membranes of cell walls when you have a different potential inside and outside the cell. So you create pores, like this simulation here. You create pores, so the microorganisms now cannot really control what goes in and what goes out the cell, and that creates the inactivation, that leads to inactivation of the microorganism. So what this side effect does is, if we compare here a conventional heating, like it's like pasteurization of milk. So you have very low temperatures here. And if you compare in the same temperature, you see that the decrease in the viable microorganisms is always faster for the ohmic heating. So as you heat it, you get more reduction. And we can see here when we compare the d-values, for those that are not familiar with, as the time required to decrease 1 log in the microbial count. So if we compare conventional heating and ohmic heating, at the same temperature, you'll see that ohmic is always faster than conventional technology. Although heating is the major effect, we do see side effects. So the benefits of that is that heating is fast, and heating is throughout the volume, which means there's no hot surfaces exchanging heat. So what we can get from there is when you have conventional process, you have steam or hot water normally generated outside the plant. You're burning fuel, you're producing steam, you're pumping it into your plant, and you're losing a lot of energy. And then you have to exchange that heating with a surface. So that means a lot of compromise in quality and energy with the nutrients or colors or sensory properties. Although when you're heating with ohmic, it's an on-off technology. If you're processing, you turn it on. If you're not, you turn it off. You're not spending energy. And it's a volumetric heating, as I said. So the whole volume is heated at the same time, which is a real benefit. And you have simultaneous heating of liquid and particles. In conventional technologies, if you have like a soup or a fruit pulp with pieces on it, you first heat the liquid, and then the liquid hits the particle. which takes time, and you decrease the amount of nutrients or sensory properties. But when you heat it ohmic, everything is heated together, so the inner of the particle is heated at the same speed as the liquid does. So in terms of quality, it's really interesting technology. Unfortunately, I couldn't bring you sensory or sensory evaluation of those products, but I'll show you some of the high pressure ones. So moving into a non-thermal technology now. High pressure is probably the most commercial one available. There's a lot of countries already using it. And it's really simple technology. It consists in applying and giving pressure throughout the product. You normally have like an autoclave, a vessel, a big vessel, where you put your food inside already packaged in this final package, and you pump water into this vessel, and you get really high pressures. And this is quite simple technology in terms of food science, not engineering, but food science. So what it does is pressure induces physical, chemical, and biochemical changes in microorganisms and some food components. And what's the nice of this technology is the isostatic principle says that the pressure is evenly and immediately transferred to food. So there's no such things like thermal processing that you have a thermal profile. Pressure is immediately in the whole volume. It doesn't matter if you're processing 100 mL or 100 liters. It's the same effect. So this is really good in terms of processing, in terms of engineering. And you get improved food safety and food security due to inactivation of microorganisms, or even they are deteriorating or pathogenic microorganisms. And it's processed in the final packages. Again, it's an on-off technology. So if you're using, you turn it on. If not, you turn it off. In terms of sustainability, is very good. Normal processing conditions that we see in the market for microbial inactivations around 6,000 atmospheres or 6,000 bars. Processing times are really short due to the isostatic, the principle that I said. So when you pressure everything at the same time, so you don't need really high processing times. And the processing temperatures are really below 40. And I'll give you an example that is different. So what we get most of the time is pasteurization. So we're not killing spores so far. I'll show you at the end that we already started to do that. So what we do is we're changing what happens to the food components. In terms of protein, we are unfolding it sometimes. So we have a lot of work done that we modify enzymes, or we can increase or decrease activities of enzymes. We can change proteins. A colleague is going to tell you more about that. But we can change emulsifying properties. We can change water holding capacity of proteins, and you can get new products out of that with the marketing increasing into the vegetarian or vegan products. That is quite interesting, of modifying plant protein to get new function properties. We also did some work on allergens. We can change the proteins that produce allergenicity, so they're easy to break down by enzymes. And we are also proposing a new project now on the immunoglobulins from mother milk. So today, if we pasteurize mother milk using high temperatures, you losing a lot of immuno properties, and when you process with the high pressure, you don't really lose it, or we hope not. In terms of polysaccharides, you can see some changes on starches mainly by changing its properties. We have also some work done on the gelatinization of starches and even producing resistant or slowly digestible starches by physical modification. It means you don't need an E number when you use it in your product. And as far as nutrients are concerned, there is no effect on the molecules, so you keep your nutrients as they are. And the side effect is high pressure facilitates the extraction of these components from the cell walls. So I'll show you some results. So you increase probably bioavailability of these nutrients. In terms of market drivers, what we see is that the technology couples with the FTA 5-log reduction for pathogens. It's really interesting in terms of nutrition because there is no damage to bioactive compounds. It increases shelf life, which for food security is a gain, and is the raw taste that really is taken into the consumers. Just to show you some examples of food safety. This is a beverage that has a quite high pH. It's close to 6.5, I guess. And it was inoculated with E. coli, Salmonella, and Listeria. And you can see that after processing, HPP processing, it was possible to reduce like 5-log reductions. And they maintained like this for at least 60 days, which is a really interesting gain in terms of exposure at the supermarket. My time is running. Same here for roasted beef. You can see that for the same microorganism, there was a reduction. This number here doesn't mean it's still microorganism there. It's just that the methodology does not allow us to say that's 0. But again, we could see like 100, almost 120 days, the product was shelf stable. This was a project we did for sodium reduction. Of course, consumer wants that, but we cannot forget that sodium is a preservative. So if we take out from the product, it's more difficult to keep it safe. So we did that. We inoculate Listeria into a turkey ham, sliced turkey ham. And again, we could get like 8-log reductions in this, which is quite interesting. For this kind of product, it's even more important. I've been to a company in South America that they had Listeria in their sliced ham line. And if you're aware of that, you can put all the things down, you can clean it, you can mount it again, you never get rid of Listeria. So the authority of that country agreed that if they had a HPP machine at the door, so any product that was produced inside, it was going through the HPP, they would allow them to produce, and they are producing now, and free from Listeria, which is good. In terms of nutrient, these are examples for orange juice. You can see that no matter the pressure is, you always have the same amount of vitamins, folic acid, niacin, or whatever. This is comparing three types of processing juice, orange juice. HPP, flash pasteurization, and a pasteurization that's lower temperature but long time. And if we compare only with C vitamin, you see that the fresh juice is the same as HPP. This is a work we've done to Jaboticaba is a Brazilian superfruit. There's a lot of biocompounds, bioactives on the peel. And we tested the juice, pasteurized juice, and HPP processed juice. And here's the total phenolic compounds. We had an increase of 35% extraction of this material from the cells, which increases the total phenolic compounds. The same for the anthocyanins, which is a nice blue color, reddish or whatever. Again, for the HPP, we got an increase comparing to the non-pasteurized juice, almost 100% extraction of those materials from the cells. And the same for the two antioxidant methods, OREC and FRAP. You can see that antioxidant capacity of the HPP processed juice is much higher than the control group. The same for Açaí pulp. I guess most of you are familiar with Açaí. It's also a superfruit. And we did the same, again, for the anthocyanins. And this time, we processed HPP at room temperature and a higher temperature because we were trying to sterilize it. So we got high temperature, not too high, but higher temperature, and we got like 5 log reduction of a spore. And again, we could get increase in anthocyanins, an increase in polyphenol and phenolic compounds, and again, FRAP and OREC were always equal or higher than the thermoprocessed. And this product also have a problem with color. If you thermoprocess it, it changes color a lot. In terms of sensory, no matter what we say about consumer, price is important, healthiness, convenience, sustainability. Taste is everything. Our keynote speaker yesterday said, we're not eating pills, we're eating food. And taste is still really important. And in terms of this technology, if we compare orange juice processed by HPP or heat, you see that the flavor profile for the fresh juice and the HPP juice are more or less the same, comparing to the heat one, which is completely different. The same for the Jaboticaba juice. We even improved the taste from the fresh one. And the reason is you're extracting more compounds from inside the fruit, so it gives you better flavor, better texture, aroma, or whatever it's meant to be. And this is for coconut water. You have a lot of coconut water in the US market now, so if you try to heat process it, for us food engineers, it's the worst product to process. You lose nutritional properties, but you lose taste if you try to process it. Whereas HPP, we did that with more than 100 consumers, and you see no difference. People cannot spot which one is processed, which one is not, so which is good in terms of taking it. Fruit, fresh fruits. There's a company in Brazil that produces fruit salad every night. They ship it to UK to be sold in Sainsbury. And every day they have to ship it. They're not HPP processing it. I'm trying to convince them, but they ship it, so the product won't last more than 1 day at Sainsbury. So if we do that, you're probably getting the same product, but longer shelf life. And what we're doing now, we're trying to sterilize products using HPP, what's called pressure-assisted thermosterilization. So if you get a retort, like a baby food, you process inside the retort, it takes time to achieve the temperature, so you're losing compounds there. And when we HPP it, there's a trick that I didn't tell you, but the temperature increases like 3 degrees Celsius per 1,000 atmosphere. So if we're talking about 8,000 atmosphere, we're getting more than 25 Celsius degrees. But it's instantaneously heated. And as you release the pressure, the product cools down immediately. So in terms of sensory properties and the losing of nutrients is really interesting. So we're almost getting there. And also, less formation of undesirable compounds like hydroxymethyl furfural and other compounds. So the key takeaways of that, I'm finishing. Food processing is essential to ensure food security. We cannot live without processing, although some artists on the TV say that it's possible that everyone is going to cook inside in our homes. Is not possible. We have people talking about waste in the following sections, but by 2050, we need to grow 60% of what we produce according to FAO. And increase in agricultural is not sufficient. We're still wasting 30% of what we produce. And I think that if we process, and processing is still only 6% of waste of what we produce, if we improve it, probably we're improving these numbers also and handling distribution and consumption of wasting material. So we need to process. There's no way out from there. And emerging food technologies can deliver food and fulfill the sensory and the health demands of the consumers, and we can prove it. The major problem with the technologies is still communications. If I come here, I'm speaking only for 200, 300 people, and any nice-looking artist goes into the blog or Instagram and connects to thousands and millions of people immediately. So we're losing that battle. And for you, from the companies, you have to understand that people now want to know, understand how food is produced. Of course, labels is still important, but it's increasing the demand for transparency. I saw a few days ago, there was a survey, 85% of the consumers want to know how food is produced. So our consumers are becoming extremely confused. They want transparency. We need to simplify communications. Consumers are not our peers, so we need to improve that. And we need to put together more of the scientific areas. And just to end, I saw that a few months ago, and it's not because it's America. I mean, in a country like this, if we have the level of education and communication in this country is really high, and we still have more than 20 million people think of this. Imagine other countries like Brazil or anywhere else. So we need to improve communications in terms of emerging technologies. Thank you very much. I thank for some of my colleagues and students and for the organization for the opportunity. Do you take questions? Yes.
We have time for 2 or 3 questions, very short. Please.
Please. Yes.
Good morning, and thank you for a really enlightening presentation. I like particularly your last slide. My question for you is, a lot of this work generally is done on pathogenic bacteria. But more and more, as we begin to look at these non-thermal interventions, the question of viruses comes up over and over. And in areas like dairy, raw milk, for example, Coxiella has always been used as the standard. You must kill Coxiella in order to demonstrate pasteurization. But in a non-thermal process, and when viruses come up, I'm finding that there isn't a lot of information out there on specifically what viruses are going to be a concern in raw milk when you're talking about non-thermal interventions. Any comment at all on that?
Excellent. Yes, we're still struggling with that because the simpler the microorganism, the more difficult it is to kill. And that serves for most of the technologies. And this one is the same. So for virus, we're still struggling with that. And maybe the pressure-assisted thermal sterilization will help that. But I don't see many works done in terms of inactivating virus. You're right. For the Coxiella, for all these, pathogens or whatever, surrogates, we're finding surrogates for all the foods, and it's quite easy, I would say. But for virus and spores, we're still struggling. maybe this pressure-assisted technology will couple with that.
Thank you, and I apologize. I forgot to introduce myself. I'm Edith Wilkin with Leprino Foods.
Thank you.
Thank you.
Good morning. I'm Mike Doyle, retired from the University of Georgia, and thank you for a terrific presentation. It was a nice overview for HPP in terms of what it can do for beverages, but it's being perceived as a panacea for all foods, and there's work that has been done. When you add a little fat to the product, it causes oxidation. You can get off flavors like you get when you irradiate foods. And so I just want to caution that we don't want to oversell this as a panacea for all foods. Try it with some ground turkey, for example, and you give it a 5-log reduction for salmonella, and you get the same response from a sensory standpoint as you do irradiation.
You're right. For the high-fat food is still a concern, although most of the scientific results I've been seeing, because what the professor mentioned is that oxidation can occur and increase oxidation of really high-fat products. It does, but again, there's a lot of engineering things going on, so low temperature also helps that. Good packaging system helps that. And of course, really high fat content products will oxidize faster than and this product I showed, the turkey one, we used carvacrol as an antioxidant and an antimicrobial compound. It helped a lot. So consumer didn't feel the difference after 2 months.
Please, the last question.
Hi, Liz Specht from the Good Food Institute. Thanks for your talk. I especially enjoyed your comment about improving potentially the functional properties for some of these plant-based proteins, because that's a struggle in that industry. But at the same time, you mentioned potential to bring out some of the flavor compounds, which can actually be problematic for some of these plant-based proteins that have bitter or beany off flavors. Have you observed cases where this flavor extraction kind of property has been detrimental?
No. When we process the protein isolated, is a real problem. If you process products, it's within all the things we've done so far in all the literature, apart from the oxidation with the fat, I never saw any comment on flavors. On the opposite, it always enhances texture and enhances a flavor. Also, enhances sweetener, the sweetness of products, some of the products. We saw that consumers, at least in the first few days, consumers are rating it as sweeter. But then for some products, it goes at the same level very fast, and some of them they're not perceived.
Thank you.
You're welcome. Andy?